All right, everyone, welcome to office hours. Thank you, everyone, for showing up. We're just going to wait another 5 minutes or so to let other students roll in who might not be able to. All right, everyone, welcome to office hours. Thank you, everyone, for showing up. We're just going to wait another. Oops, and if you heard an echo, I apologize. I have the Google Hangout up on another screen to let the live chat run, but we're waiting another few minutes for people to roll in. All right, it's 5 after the hour, which means it's time to start office hours, everybody's favorite Wednesday evening show. Thank you all for coming. I see a lot of faces watching, certainly more than I expected. The Wednesday after problem set 2 was due. So I've got, as always, a bit of prepared material based on the questions asked on Piazza, and then I'll have some time for open questions at the end. Just so everybody is aware, this broadcast is being recorded. If you're in the Hangout and you want to talk, you're welcome to, but that will be recorded and made available to the class afterwards. You can also ask questions in the live chat on the YouTube live page, and I'll try occasionally to check back in on Piazza, but that'll be intermittent. My screen only has room for so many windows. So with that said, I'm going to pull up my presentation and let's get started. All right. So today we had questions on a few different topics, and I picked and chose. So I'm going to spend a little bit of time talking about the Hopf transform one last time, and then we'll sort of put that behind us as we move on to other assignments. I'm going to answer a question asked by Jean about exploring problem set 3 techniques, what works, what's a good idea to try. I'm trying to be a little circumspect there, so I have some ideas and a set of results. Then I'm going to spend just a tiny bit of time covering something near and dear to my heart as a math major, which are some linear algebra functions in NumPy. I didn't get any questions about that, but I think it's important for the later parts of problem set 3, and so I wanted to bring it up now and maybe for once get ahead of some of the questions. And then finally, we'll probably have about a half hour for open questions. I'll also try and answer a few Piazza questions that arrived after I had the slide deck put together. As always, feel free to ask questions during the presentation. I'll also try and do my best to stop and solicit questions. Let's get started. Okay, so there were a few questions that I wrapped all into one that were summarized. What's the point of problem set 2? There's a lot of painful parameter tuning. Why did you ask us to do this? And I wanted to spend just a moment addressing that, because I think as students, you do have a right to know what we're thinking and what our educational objectives are with these problem sets. And the meat of it is the Hopf transform has been important in computer vision for a long, long time. Hopf patented the method in 1962. I actually think that's a really fun patent to look up and read. In particular, it's not going to be super clear on the internet video, but his setup involves 2 television cameras, an oscilloscope, some analog electronics, a magnetic tape recorder, and finally a computer. So if you thought problem set 2 was bad, be glad you weren't Hopf doing it with 5 different analog electronic setups and 2 television cameras. And the Hopf transform has been used in various computer vision systems fairly regularly up through at least 2006, where it was used in some papers for street sign detection. I also think this is a great paper for anyone who's curious about how Hopf might be used in a real street sign detection operation, to take a look at that. They do many things that are similar to what you guys did in problem set 2. They use color to help distinguish signs. They use line angles to try and find yield signs, and they use a circle detection to try and find stop signs, as well as do not enter round type signs. They also do some more complicated recognition, a technique called histogram of gradients that we'll talk about later in the course, and they have some neural networks that help with recognition, as well as Kalman filters, which are all topics we'll cover later. But the points I wanted to make here are, 1, yes, there's a lot of painful parameter tuning. That's somewhat the nature of computer vision. 2 generations of graduate students have worked with Hopf tools and sort of been through the same amount of twiddling parameters, changing the size of the accumulator array, and so on. So we don't ask you to do it just to make you unhappy. We ask you to use Hopf tools because we want you to develop some intuition for these tools that have been a pivotal part of computer vision for many years, as well as an understanding of their limitations. Much modern work in computer vision, machine learning-based work, was inspired in part by frustration with methods like Hopf and the seemingly endless number of tunable parameters you have to deal with. So I think that's all I'm going to say about why problem set 2 And I'm going to skip ahead to the next problem set 2 question we had, which was how to get good results from Hopf circles. I think this was something many people struggled with on the problem set. I'm not sure if I have the greatest of answers, but when I sort of look through some work, and also thought about it a little and did some of my own sanity checks. Hopf circles works if you give it circles to find, and it'll work with a fairly wide range of parameters, but it has to have a fairly high quality input. And so filtering is important, and in particular, setting the Hopf circles parameters for canny is important. I think many students passed a canny edge image into Hopf circles. I've done some looking at that, and I believe that that's generally counterproductive. Hopf circles has a built-in canny. You do want to run canny so you can see what Hopf circles is seeing internally. We have a comment from Senthil Kamaran who says, I can't hear anything. Is that true for anybody else in the video chat? Okay, it seems like the problem is on his end, which, thank goodness, I'm glad I didn't just talk to nothingness for 10 minutes already. So coming back to Hopf circles, I run canny to see what Hopf circles is seeing, and Hopf circles is running canny internally on its input with an upper threshold set by parameter 1 and a lower threshold set by parameter 1 divided by 2. And as an example of why Hopf circles might have some problems, if you give it a grayscale image like this on the left, it's very hard for Hopf circles to see these traffic lights. In fact, it's hard for us to see with our eyes, or for me to see some of the traffic lights. And so the edge image that actually gets passed in, it doesn't find a strong enough gradient there to find an edge, and ends up with sort of 3 real circles and a stop sign that also looks a bit like a circle. And when I run Hopf circles on this image, it finds the circles it's able to see. It doesn't find them perfectly. The radius is a little off on some. And it doesn't find the stop sign as a full circle. It finds sort of one edge, which is actually the algorithm behaving appropriately. It gets the most votes for a circle that sort of traces the edge here and gets a little bit of the edge there. But generally, if you pass Hopf circles a fairly good input, you'll get a decent output, but it's not going to be perfect. If you're using these Hopf algorithms, you've got to assume that you're going to get somewhat imperfect output, not exact radii, maybe not exact centers, depending on exact parameters. And if your pipeline can't tolerate that, you have to sort of move to a different technique. And that's all I have sort of talking about Hopf circles, but I sort of hint here that problem set 3, we're really trying to edge everyone towards different techniques. We've done Hopf very deeply in the past, and you've all spent 2 weeks understanding its intricacies. So in this grand, fun whirlwind tour of computer vision that Professor Bobak is taking you on, we move on to some other methods of finding objects. And I'll talk about that next, but I want to take a brief pause. Does anyone have questions about problem set 2 or the Hopf transform, particularly Hopf circles, at this point? All right, seeing no questions, I'm going to jump onwards and talk about problem set 3. The challenge I always have talking about a problem set we've just released is how much information can I give out without doing the problem set. So here I've settled on a frustrating compromise, which is there are a number of techniques mentioned in lecture sort of between the end of Hoff and where you're supposed to be at the end of the next 2 weeks. And they include sort of corner finding techniques and template matching techniques. And we'll also keep in mind sort of the Hoff tools techniques we've learned. And what I've done is I've taken one of the input images from the problem set. I believe this is sample noisy 2. I'm not sample sim noisy 2, but I'm not remembering the exact file name. It's a file you have. And I sort of processed it in 4 different ways. And the 4 ways are Harris, minimum eigenvalue, template matching, and canny. And I'm showing all 4 results here, but I'm not going to tell you which is which, because we, the TAs, want you to explore and sort of see the differences between these on your own. And I'm going to go look through these images and sort of discuss, is it easy to extract the exact center of the circle from this image? We have a very tight auto-grader tolerance for this, in part to discourage some techniques like Hoff circles. You must be within 2 pixels of the marker just for this first auto-graded section with the simulated markers. So if we take a look, this image looks like it's extracting edges, and this might be passed to something like Hoff circles. The problem is it's pretty hard to clean up. If you apply some filtering, which I've done here, it gets rid of all these circles, but it also gets rid of some of these outer edges. You might be able to still pass this to Hoff circles and get a decent result, especially if you're tuning your radius well so you're not finding little circles here. But it's going to be tricky to actually get a fit to this circle. Vitaly asks, what are we looking at? So just to reiterate, I've taken one of the sample images from problem set 3 that we're asked to process. That's on the top left. And then I've processed it 4 different ways to try and show different techniques from lecture. I'm not going to match techniques to images because I want you guys to explore, but I will name the techniques so you can generate your own images. We're now looking at the upper right image. I'm trying to indicate that with my mouse pointer, but it might not be coming through super well, so I'll try and also use words there, which is an edge image that we could pass to something like Hoff circles. But looking at this, I have some doubts as if we can really get a 2-pixel tolerance. So coming down now to the middle image on the left, this is interesting. Immediately we see we've got some bright patches in the center of each of the circles, so there's a correspondence there. We've also got some other bright patches, though, that might be confounding, and those actually appear right at the corners where the black area ends of the circle. So this is interesting. The center bright patch appears to not be exactly 1 pixel, but you could probably do something with this, possibly averaging points, doing a little bit of maximum finding or fitting. So this looks like a usable solution. If we pop down now to the bottom image on the left, it looks very similar to the top image, but the peaks aren't as pronounced. They aren't as bright. And in particular, it's not always clear that the center is the most distinct peak in this processed image. So given a choice between the 2, I'd probably choose the top one to work with. And finally, if we come to the right here, this is very encouraging if we're trying to find markers in the image, because there's one very, very bright pixel at the center of each marker. And so as a starting point, if I ran each of these 4, got these results, I'd pick the technique that gave me an image like this, work with it, and try and anticipate if there are going to be problems with the brick wall later. But this looks like a good bet for passing the auto grader. It's up to you guys to figure out which of the techniques will give you an image like this instead of an image like this, this, or this. So I've done my best to be a bit confusing, but and not just give out the answer right away. Vitaly asked, why is the one on the bottom right better than the one on the top right? So if you look at the one on the top right, it's hard to pick out exactly where the center of the image is. These lines end up not quite meeting in a number of cases, and it's also not clear they're meeting exactly at the center of the image. They might be off by a couple pixels. That's a little more clear if we zoom in on the top right. To get a center from something like this, you'll often have to pass an image like this to Hopf circles or Hopf lines. And it can be hard to get a 1 or 2 pixel accuracy out of something like Hopf circles or Hopf lines. For the problem set 2, we had an auto grader tolerance of about 5 pixels, and that was often difficult in and of itself. So looking at why do I think this one on the bottom right is good, there's a single very bright pixel that corresponds to the center of each marker, and you can do a pretty good job. Cassie asked, did you say we will not use Hopf circles for this problem? It is not our intent to have Hopf circles. If you read the section of the assignment description that talks about methods, we'd prefer you use methods from the next section of the lectures. I like to think of this class as the whirlwind tour of computer vision concepts. So we've sort of spent some time on Hopf, and we'll be moving on to the next topic. Omar Levran asks, is there a reason not to use cv2.goodFeatures to track? Not that I'm aware of. I will caution that we might need to check that function internally and make sure it's not solving the problem set in just one go. In general, we don't want to have any functions that you use and they give you the answer to the problem set immediately. So CV2 good features to track, we'll be looking into that internally. I don't make any blanket logistical pronouncements in office hours, but I would be cautious basing my entire approach on that. Yeah. Okay. So before we move on to a bit of linear algebra, does anyone have any more questions sort of on techniques you might use for problem set 3? Will Chen asks, how did I draw these images? I made a quick little script that much like the what do we call it? Do we call it example.py? No, gosh, experiment.py. I made a quick little script much like that where I load some images in, I process them, I normalize them, and then I do cv2.imwrite to write them out. While I'm working and getting the images looking right, I typically use cv2.imshow and a wait key to sort of click through them all quickly. Each of these images is generated fairly succinctly by passing the input image here to cv2 functions related to the material in lectures 3 and 4. So Nate asks, would the markers be rotated? I do not believe that the markers will be rotated for the auto-graded portion of the assignment. However, if you look at some of the videos and examples coming later in the assignment, it's pretty clear that the markers are rotated. You'll have to make your code robust to rotation, which can present challenges for some of these methods. For example, template matching doesn't by default have a rotation invariant property. You have to build that in either by checking multiple angles or by being clever about your template. All right, Vitaly asks, which tools methods should we explore with this problem set? Really, that's covered in the problem set instructions, so I'm going from memory here, but I believe it's feature detection, template matching, Harris corners are sort of the techniques and ideas you might want to look into. Robert Horn asks, what is the point of having images with noise in this problem set? It seems we've already solved that in the last assignment. Doesn't add any value to this one. All right, so computer vision noises is always a problem, and in general, I don't trust anyone's results with a computer vision algorithm unless they've shown it to me in a situation where there is noise. You often see people present great results that completely fall apart in the real world because there's either sensor noise or there's environmental noise. And so we're pretty much always going to ask you to prove your algorithms on images with noise. It's sort of standard practice in computer vision. All right, got two questions coming in. Vitaly asks, I mean specific algorithms. I think at this point, this early in the P set, I don't want to dive into specific algorithms. The points of these problem sets are for you to explore everything. All the bits and pieces you need are in the lectures, and it's up to you to figure out, one, which pieces are best, and two, how to chain them together. Okay, and the other question that came in, general topic question. As we work on the assignments, can we request our code for review by TAs privately, especially if you are stuck? Our course policy is generally that if you post a private message to us, we will take a quick look, but we aren't providing deep code review, and you'll often get a comment back. Some people who watch this at some point may have already seen this, where I suggest a number of debugging techniques or avenues to explore rather than a detailed fixed line 10 of your code. We just don't have the TA manpower to provide, in-depth debugging for everyone. All right. Last call for additional questions before we move on to some fun linear algebra. All right. So the second half of this problem set, which I think is honestly the more fun half, asks you to take your images and apply some linear algebra to solve for a homography transformation matrix, and also to warp pixels from one image to another. And I know in the past, this has been mildly disconcerting, and people try to implement very complicated algorithms that are already available. So I just wanted to point out that NumPy does have a linear algebra module. And in particular, there are some nice functions in there. Solve, which solves systems of equations that are exactly solvable. So number of equations matches number of unknowns. There's also a least squares solver, which can find solutions to systems of equations that are over-constrained. So you have more equations than you have unknowns. It can also solve the same systems that NumPy linear algebra solves. Finally, in lecture, Professor Bobek discusses some singular value decomposition-based techniques for solving systems of equations where you might have an element that's set and you don't want anything to blow up, so a poorly conditioned inverse problem. And so that's available NumPy linear algebra SVD. And finally, the function NumPy dot will multiply two NumPy arrays as though they are matrices. And lastly, this problem set involves some fairly large images. If you have an image that's 1,000 by 1,000, you now have 1,000,000 points in the image that you're going to have to process. And I wanted to point out a matrix multiplication technique for doing a lot of calculations at once quickly. So you may come across a scenario where you have a matrix A and a bunch of column vectors. So we'll call them x1, x2, x3, and we're going to say you have up to 1,000,000 of them, so up to x 1,000,000. And you want to multiply each of these by A to get out your new vectors, which we'll call y. So sort of the intuitive version that matches the words I just gave is to take A. So here I'm randomly generating A and I'm randomly generating X. So I have some data to use. Allocate some space for Y, and then sort of iterate through and take each of our column vectors from X that are all packed in a big array and do the matrix multiplication and store it in Y. But thankfully, because of the way matrix multiplication works, we don't have to do all that. We can actually just multiply A by X, which is all these column vectors stacked up into a long, so it has many columns and 10 rows matrix. And the advantage here is, the reason this is fast is, one, we're avoiding a loop, which is always slow, and two, modern processors are incredibly optimized for doing matrix multiplications and other linear algebra operations. It's a big focus of systems operations, is having fast routines for this. So here we do, on the left, a bunch of small matrix multiplications, and on the right we do one large matrix multiplication. And our system is able to do this in an optimized way. You get almost a 40 times speed up by processing your points as a matrix multiplication rather than 1,000,000 matrix multiplications. That's just, it might come in useful in this assignment, so I thought I'd pop it up. We like to see code that runs quickly, because otherwise, when we run it, we have to wait a while. So finally, we have one more question, which is, our topics in the book seem not to be related to the assignments. Is it true, or should I dig deeper? Gosh, I'm going to confess that I haven't looked at the book readings recently. The topics in lecture are definitely related to the assignments, but they're related in the following way. We expect you to take ideas from the lecture and apply them to the assignments. For example, in assignment 2, which many of you have finished, you're taking the Hoff-Tools ideas and you're applying them to finding circles and lines. You also take ideas like filtering and some of the other linear operations on images, and images as a function from the early lectures to build inputs to your Hoff-Tools. Understanding what's going on in lectures make the problem sets much less frustrating. At least as a TA, I have to say that, and it's also my honest opinion. So really, that's all I had pre-prepared. I wanted to take a brief moment to also address one question that I saw on Piazza but didn't have time to prepare an answer for in slides, which is from, one moment, and I'm glancing off screen here to find Piazza. Yeah, so we had a question from Jean-Louis about ideal points and lines. I'm going to defer that one till next week, because I feel I need to have at least a diagram to have any hope of explaining what's going on there, and I also need to go back and review it myself. And the second is about Gaussian derivatives at each pixel in the Harris detector algorithm. And Jean-Louis correctly notes that CV2 corner Harris has parameters for the Sobel function, and the question is, Gaussian derivatives here means Sobel operator convolved with a Gaussian window. Is there a way to tune the parameters for the Gaussian function? And the answer, as I understand it, is that the CV2 Sobel operator includes a convolution with a Gaussian for sizes larger than 3 by 3. So if you have a 5 by 5 or a 7 by 7 Sobel operator, the reason that operator has gotten larger is a differentiation has been convolved with a larger Gaussian. So that's in some ways built into the larger CV2 Sobel operators. You don't have a lot of fine-tuned control over that Gaussian, and it's also limited in size. I think there's a maximum of 7, although don't quote me on that. So if you want to have more fine control about how the image is being blurred, it's perfectly fine to convolve the image with a Gaussian and then apply Harris corners to it. It's slightly less inefficient, but the slow part of your code for this assignment isn't going to be a convolution with a Gaussian. So that's my answer to that, and I'll now open the floor for questions from anyone. Vitaly asks, do all the parts of the assignment have Bonnie tests, part 1 through part 5? I don't have that open in front of me, but it's the parts which have autograder tests are mentioned in the autograder post on Piazza. You can also there's no penalty for submitting early and often in this course. So feel free to make a submission. Everything's going to fail because nothing's implemented if you haven't started. But you'll get to see the autograder output immediately and see where there are points and see which functions are being graded by the autograder. Yeah, Vitaly says PS2 did not cover everything, and that was a surprise. I highly urge everyone to sort of read through the minutia of the problem set descriptions, because we often include a note buried in there about which parts are graded by the autograder and which are going to be graded manually. Running a class is complex, and we do the best we can. The next question I've got is from Omer, which is, for the algorithms you showed, were there pre-processing of the images like blurring, or strictly the algorithms? I'm assuming this is about the sort of problem set 3 approaches images where I showed 4. I pre-processed each image as would be appropriate for that algorithm. That means in some of the images, I think I applied a small medium blur, and in some of them I didn't. Certain of the algorithms we discussed are very robust to noise and certain aren't. So for one sensitive to noise, I did some median blurring. I chose to use a median blur on those images because we want to preserve the sharp edges in the marker, and a median filter is edge preserving. I worry, and I haven't tested this out fully, but I worry that with a hard Gaussian blur on the input images, you end up blurring that nice center point that we're asking you to find of each marker and making it harder to find. But I'm certain someone here will use a large Gaussian blur and prove me wrong. That was just my intuition, that it would be more difficult. How much time should we expect to spend on this problem set 3 as opposed to problem set 2? That's a very hard question for me to answer. My gut feel is I look at it and I think it's slightly easier and might have slightly less parameter tuning. I'm also a mathematics guy. That was one of my undergrad degrees. So I look at the linear algebra parts of this problem set and think, fantastic. Like, what a joy to get to implement some of these algorithms. I think other people look at it and say, gosh, this is very frustrating to do the linear algebra, and it might take them longer. So it's going to be fairly personal. I'm not seeing a ton of questions rolling in, so I'm going to turn the tables and use this as an opportunity to poll the audience about how certain things in the class are working for you guys. We're always trying to improve what we do and improve the learning experience. So my question is, what sections of the lectures are clear and making sense? And are there sections of the lectures that aren't clear or aren't making sense, that Professor Bobek is moving too fast, moving too slow, anything like that? We have one comment that they wish masking was covered more in depth. I'm actually going to note that down for the course, because we've moved some things around this year, and I think Bobek spends quite a bit of time covering color, but it's in lecture 9, which is kind of or section 9 of the lectures, which is kind of the odds and ends, where Bobek quickly covers everything he feels is important, but wasn't covered earlier in the course. We also have a note that parameter tuning is a bit difficult, or it can be frustrating. I empathize. I've taken this class personally, and there is quite a bit of parameter tuning. It's also somewhat the nature of computer vision. Is the nature of computer vision is parameter tuning, and it's hard to get away. So the question is, I presume that's expected, but what is our learning intention here? The learning intention with parameter tuning is to build intuition for these algorithms, and also to build intuition for tuning computer vision algorithm parameters. It's the nature of the field that if you're going to do a lot of computer vision work, you're going to be tuning parameters, and we don't want to hide that from you in our problem sets. We want to offer you the chance to build very exciting working systems that get as close to the real world as you can. We always try and have challenge problems that are either good simulations or working with real world images. And to get success in those areas, you have to tune parameters. I'm seeing a resounding flurry of working code examples requests. So I'm also making a note of that. Again, I just want to, I'm trying to get feedback here that I can pass along to the rest of the team. Please don't interpret anything as a promise of immediate change or shift, but I do appreciate all the feedback, and it's something we'll look into, if not this semester, possibly next, but we'll also try and do the best we can with the resources we have. All right, well, Vitaly asks, is it possible that we can link the CV2 demo example that exists today to the problem sets? Somewhat. We're generally trying, this is not a course on, I've got to think carefully about what I say here. The goal of this course is to teach you about techniques in computer vision and let you apply them. So I'm a little leery of going very deep into the lots of programming tutorial sides of things. A part of what makes this class tremendously fun is all of the math, and I would worry about crowding that out. I also don't have the power to make changes at that level. Okay. Yeah, I think I've gathered some good feedback here. I appreciate everyone. I think I'm going to move on from this and call for other questions related to course material rather than suggestions for the course. But I thank you all for posting things. Omar asks, is there going to be an example for PS2 of how one of the TAs/students did it? Since there are many approaches, learning new different techniques from what I did would be awesome. So I'm just going to echo Pedro's answer from Piazza that we've looked into this, but we use assignments again and again for many semesters. So it's unlikely that that's going to be possible. We certainly can't release anything until all of the extensions that are outstanding have been complete. So stay posted on Piazza, but I wouldn't be hopeful about that. It's unfortunately one of the constraints of this program. All right. With that said, it looks like we're out of technical questions. I've gotten some good feedback of what people see as challenging in the course and what's working well. So I think I'm going to call an end to office hours here about 10 minutes early, which will give me a little bit of time to post the slides in the video. Thank you all for coming. I know it's the middle of the work week, and I really appreciate everyone who shows up. Best of luck with problem set 3. I hope everybody has fun. See you all later. Bye.